Hello, Pierre-Marie.
Well,
It's really a pleasure to have you here. You have a most interesting career. You held the world record in nuclear magnetic resonance imaging, right? With
Yes.
the best pictures, the highest quality pictures. And but you had also a second career in astronomy, if I may say so. So you discovered that there is a fundamental flaw in one of the most basic laws of physics, Kirchhoffs Law, and that had dramatic consequences for the sun. So it appears that, solar physicists are mistaken for more than a century in their solar model, and you provided very good evidence that the sun is indeed not gaseous. I think it's really big accomplishment. We're not at the end of the revolution, maybe, but I would like to start where the connection of these two fields is. I mean, at first it seemed to me that there was no connection at all between these two fields, but actually there is one, because it's when you had the idea that 8 Tesla, the very strong magnetic field, would be possible. So there was a concern that it wouldn't work. Could you comment on that?
Okay, so I guess the beginning is to talk about that MRI is a thermal process, and most people don't recognize that this is. You know, normally when we think of thermal radiation, we think of the infrared. We don't think of that some process in the microwave or in the radio region, in ultra-high field region, could be also considered to be a thermal process. But basically, when the MRI was conceived, there was a belief in the MRI community that the power required to collect an image would be so astronomical you could injure the patient, and
you would fry their brains.
Yeah, it would fry your brain, and you wouldn't be able to acquire an image. So there was some people that said that you could. I've discussed this actually in a recent lecture, which people can go look at. It was Observing the Frontier in New Mexico this past February, and so you can find this lecture online. But the central thing is that MRI is a thermal process, and people had said that the power would move with the square of the field. It would take so much power to get an image, you could never get an image, and that the sequences that we would use would be just low nutation angle sequences. You know, you couldn't really manipulate the spins as you would like, as we do in conventional MRI. At ultra high field, you'd be restricted in the types of pulse sequences that you could implement, and this turned out not to be true. We were able to implement sequences that people had said would be impossible to do. But then the fundamental thing, of course, if we go back a little bit to Kirchhoffs Law.
Yeah, but if I may, the very interesting thing from a physical point of view, I mean, you were in this medical community of people who were brilliant experts in MRI technique, but you were, so to speak, remembering a basic law of physics, which is Plancks Law of radiation, and you remembered that it was not just a quadratic increase, that the radiation would go down again, right?
Right. And so the question is, you know, we should be in the Jeans-Rayleigh region of Planck's law, and so you wouldn't expect it necessarily to come down at the fields that we have, and of course, you know. The question is, well, you can never remain forever in the Jeans-Rayleigh region. This must break. And I think now people in MRI, they understand that, yes, power doesn't move with the square of the field. And so there remains some controversy as to how power moves in magnetic resonance imaging. But, you know, in the end, we were able to acquire the images, and some of the measurements that we took at Ohio State, we required less power at 8 Tesla than 4.7. This has been published, and so there were some dramatic surprises for us. Now, but in addition to that, if we go back a little bit to Kirchhoffs Law, which is that, of course, when we take modern physics, we learn that, you know, inside a cavity the radiation must always be black in an arbitrary cavity. If it's opaque in thermal equilibrium, the radiation must be black. And Kirchhoff, when this idea was formulated, of course, the radiation became independent of the nature of the walls. Now, in Kirchhoff's day, there were no resonators. I mean, you know, they studied thermal radiation, but the idea of putting phase coherent radiation inside a cavity and building resonance that didn't occur to Kirchhoff and to no one in his time. But today, you know, with lasers, we have Q values in the cavity of a laser. You're going to have Q values of 10 to the 11th. Well, clearly this is not black. So in any resonant phenomena, we depend on the walls. The wall of the cavity must not do work on the radiation we input. Whereas in a black body, in a true black body, what is happening is that the wall is actually doing work. So in a resonant cavity, you don't want work, so it's perfectly reflecting, there's no work. And the other extreme is the black body, and in the black body you can do work. So when you learn about black body radiation, you don't think about this, that nobody talks about work. They just say it's independent of the nature of the walls. And the central thing is, of course it's not, because we do have resonant cavities, and we want those to be perfect. And if they are, they will never build thermal radiation. They will maintain the resonance which we want. So there's many parts of physics where we use resonant cavities, but we never thought about it in the context of Kirchhoff. And now I'm trying to put the context that our resonant cavities exist in the microwave and for cell phone technology, in lasers, in MRI, and all these cavities which we want resonant don't really fit into Kirchhoffs law. So thermal radiation is dependent on the nature of the walls. This is the main thing that I'm trying to tell people. That Kirchhoff did make an error because he never considered the perfect reflector, and the perfect reflector cannot do work. So this is the beginning of starting to think about what does it take to get a thermal spectrum, and this is what sent me to the sun and started my work in astronomy.
Well, all these details, I mean, you have all this explained very well in your talks, in your papers. So, I mean, who really wants to know the details? I mean, they're all on the sources. But for me, the interesting question is also, I mean, you're an expert in that community, but obviously you had a very broad knowledge about fundamental physics, or you were a person who had studied these old laws, or, I mean, it's always, revolutions in science are always about putting things together, not necessarily to be brilliant this or there, but what you did, you put it together, okay? So the law of radiation, and you applied it to that. That's kind of unusual. You must have had a different take on science.
Well, part of it is like from my training. So I was always very independent, even when I did my graduate degree. So most people, they say, oh, how did he end up doing astronomy? You know, it's not really relevant. But if they understand NMR, they'll see that, you know, these techniques, we're doing spectroscopy. I mean, I'm a spectroscopist by training, and an NMR spectroscopist, and you know, the astronomers, well, they're spectroscopists as well. So we have great overlap. And at the beginning of all this, of course, is Kirchhoff's work. So, and people might not realize that, for instance, Purcell, who won the Nobel Prize for NMR, I mentioned this in some of my talks, he was also the discoverer of 21 centimeter lines in the galaxy the year before he won the Nobel Prize. So
very important astrophysical tool, that very famous, the 21 centimeter line.
So this is one aspect, of course, that there's this very almost from its inception, there was a marriage of NMR and astronomy, even though people never realized that there was. But in Purcell's own being, there was. In his own life, you know, he had married them.
So though from the content, I mean, the close connection is quite obvious, because it's the same physics. But now, if we talk now about sociology of science, but it was kind of a break that you did. In terms of you were famous in this field, and you had papers and and people with the Nobel Prize were writing introductions for your books and things like that. And now, when you discovered these flaws in Kirchhoffs Law, and when you started talking about the sun, that we might reconsider the solar model, you had difficulties, right? So it was.
Yeah, well, that's a complicated story of what all the difficulties were. But I think as scientists,
it's not automatically that they give you credit in another community. The communities of physics are very separate, right?
Yeah,
so,
but it's also not about credit. That's an important point. So when we talk about science, you know, the central thing is to bring the idea to others, and how the idea eventually gets developed by humanity. That's something completely different. Okay, so when you do science, don't worry about the credit. You know, maybe some younger generation will get the credit. The sun becomes condensed matter, not in my lifetime, but that doesn't matter, you know. So we have to focus on what is the idea and why it should be pursued for the betterment of humanity. So I think the central thing here, why did this happen? And you know, so when I did the first experiments at ultra high field, that's what made me think, for instance, of the Penzias and Wilson measurement. And this claim that we've measured the temperature of the universe to 3 decimal places. Now, of course, Penzias and Wilson, they didn't have 3 decimal places, they just had 1. But today, of course, we claim that we have it to great accuracy through Kobe. And I've disputed that. And I've had an unusual approach, that's another thing, right? And part of that is the advice that I received from people near me that knew how to do science. So
there was a close connection between the field of nuclear magnetic resonance imaging and astronomy, as you explained. But for you personally, it was a big step to being in one community, one of the most famous researchers or the developer of ultra high field magnetic resonance imaging, and people like Nobel laureates were writing introductions for your book, and but you completely gave up and went to another field, and you discovered these things about Kirchhoffs Law, and I mean, you were new in the or not even most welcome in the field of astronomy. Wasn't that difficult? Or
yes, yeah. I mean, so I tried to follow the science and follow my heart, right? And so you make a discovery sometimes, and it brings you somewhere where you never anticipated you would be. So when I built the AT, I thought, okay, well, I will spend my life doing magnetic resonance, obviously, and I was in a medical school. But when I came to realize that there was a fundamental problem here, that there's something wrong with the sun, and you know, at the beginning, this thing with Kirchhoffs Law, you know, my first statements on Kirchhoffs Law, I actually believed it was correct, right? It was only after maybe a year later.
Why one should doubt a law?
Yeah, why should you doubt it, right? So I believe that Kirchhoffs Law was initially correct, and then made the transition to realizing there was a problem, that there's an error in Kirchhoffs Law. So now people know in 2000, some people might know in 2002 I took a full-page ad in the New York Times, and in that ad at the bottom I actually praised Kirchhoffs Law. But then a year later in 2003 I write my first paper on the validity of Kirchhoffs Law of thermal emission, and there I say, this cannot be valid.
Since we're just discussing this sociological process, also how science works, that was a very, very unusual step, wasn't it? I mean, you did not publish in a regular peer-reviewed journal. You went to the New York Times and paid presumably a lot of money for a commercial ad. So that seemed very unusual.
Yeah, that was unusual, and many people thought, oh, who is this guy Robitaille? He's got some problems maybe, but actually they didn't realize. So how did this happen? So when I realized that the sun was not a gaseous plasma, I had a friend.
That's, I mean, if I may interrupt, that's really, really hard to digest. I myself, I told the story for to decades that of course the sun is gaseous, this and that is a black body, and you don't really think about. But once you think and you see the other possibility that you were proposing, that liquid metallic hydrogen model, I mean, it's kind of an eye opener. So, and but it's really, I mean, it's really a break in that
Right.
solar physics.
So why did I decide to go about it this way, you know?
Mm-hmm.
So of course, you know, when I talk about journals, you know,
Mm-hmm.
I mean, people accuse me that I don't believe in the peer review process, but that's not correct, you know. It has a place in science.
Mm-hmm.
You know, most of us, and when I was doing magnetic resonance, you know, we depend on our peers to guide us, and many times my papers have been improved by comments of
In
our
normal
peers.
science,
And
yeah.
this is normal science.
Normal science, how Thomas Kuhn would phrase it.
Yeah, but when you have a paradigm shift, then you're addressing something that you're normal, the community that would normally be open to peer review is not there, because now the astronomers are holding that the sun is a gaseous plasma, and I'm saying, no, it's metallic hydrogen, so you don't have a proper review
That sounded
community.
too incredible, yeah.
So what happened was, when I came to this realization, I had a friend who actually had trained with a Nobel laureate, and he was working in Southern California. So I flew to Southern California to spend the day with him, and we went for a walk in Huntington Gardens. People who know US.
So you were discussing that idea.
Yeah, that's why I
and
specifically.
he was discussing it openly.
Yes.
Yeah.
So we went for a walk, and then I think we spent like 4 hours in Huntington Gardens. And during the walk, we were discussing the sun, and I told him it's condensed matter and so on. And he said, "Well, you'll never publish it in the physics journal, and then nobody will let you say it." And then I said, "Well, what should I do?" And he was the one that suggested, "Well, you should just take out a full-page ad, take out an ad in the New York Times."
It's
okay,
a very
this is
unusual advice
right.
from a such a respected
right from a
physicist.
respected scientist. It was a very unusual advice, and I said the same reaction as anyone would have. Well, scientists don't publish in the New York Times, and he said, "No, Pierre, you're wrong." And actually, I guess. He mentioned to me that when photosynthesis was discovered, it was first published in the New York Times and then in the journal. So there was actually precedent for it. And so then I went home and I told my wife, you know, I want to take out this ad in the New York Times. And I called the New York Times, and I found out, you know, this is a significant fraction of money. It was $100,000, which was a huge, enormous sum for us. But I decided I would start there and place the ad in the Times, and my wife agreed that I was able to do it. And
but that's, I mean, usually one would assume that there's not much reaction from the scientific community, but somehow.
Yeah, it was different. So the rule is in science, you know, the real rule is you must say it, and hopefully you're right, but you must say it, and people must know you say it. And how is the vehicle done? Well, there's the normal vehicle. We want peer review. And then there's the paradigm shift vehicle, which, well, that's not defined. You have to use the tools at your disposition. And that's what I did and with the New York Times article. So I knew that one of my close friends in physics, it was a very eminent physicist, but I didn't tell him that I was going to do this. He knew that I believe the sun was condensed matter, but I didn't discuss my New York Times idea with him. But I knew that he religiously read the New York Times every day. He started his day, I mean, I think he couldn't go through the day without reading his New York Times. So I thought, okay, I will do it, and I'll put the ad in the New York Times. So he went to the meeting that year for the American Physical Society was actually in Indianapolis. And so on March 17th, 2002, a full-page ad appeared on page 810 of the New York Times. And the New York Times has a distribution of 2 million copies worldwide. And so I was told by friends in physics that when the article came out, you know, people in Indianapolis, of course, became aware of it. You know, it was called the collapse of the Big Bang and the gaseous sun. And so people were searching for the copies of the New York Times. And, you know, some editors came to my friend and said, no, he didn't send the paper to us. Actually, I hadn't sent the paper to anyone. because I was advised against it, I just immediately put it in the Times. It had never been rejected or something by a journal. And the New York Times article actually had two sections, which the very first small paragraph talked about the microwave background, that the monopole should come from the Earth itself, from our oceans. And then the second part was about the sun must be condensed matter. So that was the beginning of this launch of this idea.
Yeah. Well, so that's a story that reminds me a lot from Alfred Wegener, who was outside, so to speak, of the community. He was a meteorologist and proposed that continental shift, and he was not accepted at all by. What was the was there any reaction of the top solar physicists or the big
I received
it was too terrible for them. Like back then with Wegener, I suppose.
Well, what I could see, I had put a copy of the New York Times ad on a website, and I could see that as the sun was going around the Earth, as the Earth was going around and the day was moving, I could see people logging into the ad. You know, many people around the world logged into this ad, and of course it became very known in physics. And some people were upset, and other people were more cautious, and we should be thinking about this. Some people said, "Wow, he's courageous to take this ad," but you know, it's anyhow, it's what it is, and I did the ad, and I'm delighted. I don't have regrets that I opened this idea this way.
Yeah, I mean, it requires pretty much a strong personality. I mean, somehow you were fighting against the entire community of solar physicists, and you were the first putting your head in the new MRI magnet, because people were afraid it could do harm to people. So you said, I go there. I mean, these two instances, I mean, they tell you something about you. You must have a very strong character, very, I know you as a very, very polite and friendly person, but there must be some very strong force inside you. Where does it come from?
I don't know where it comes from, but I think when I was a child, you know, I'm Canadian, and when I was a child, I hitchhiked in Canada in the winter time when I was about 14, 15, and these were 1,000-mile trips. And sometimes I would be stuck on the 20 in Quebec, you know, with the road, the interstate was closed, and there was storms, and I slept under bridges. This is with newspapers in the Canadian winter while I was hitchhiking. And so, you know, I always had a very strong love of life, and also an understanding that we just have one. So you don't get another chance. So if you're too reserved and you want to be prudent about what everybody's thinking, when you have a big mountain to climb, you can't be worried too much about everybody's opinion, because you'll never climb it. So, and it's my goal is to bring the idea of that the stars are condensed matter to as many people as possible, and let them decide after I'm dead, you know. But you have to first start creating the path and the method, you know. And I think you do have to have some perseverance, and you have to be tough. And willing to endure derision from others, but it's okay. That's part of how science moves too, because you have to admit that the duty of a scientist is also to protect science. So you know, I'm not against my peers that try to say, well, you know, he's not following the proper channels, he didn't do this, or they're trying to defend science. So that's their duty, and many of them they do it, you know. It's almost as a reactionary kind of behavior without even thinking of what they're saying. So they learned when they were in the second year of physics, they learned about black body radiation. It's independent of the nature of the walls, and without even thinking about it, they said, well, everybody knows this is independent of the nature of the walls, and so on. But they don't realize the consequence in making such statements. And this is. So you have to give them time, and you have to respect what they're trying to do to defend established science. So
you're still very polite, also with the people who criticize you, I think. Yeah. So, but you didn't have a regret that you moved from your earlier field of medicine to that
Of course,
something you consider more important, more fundamental?
No, of course you have regret. I mean, if I could have, if my life had permitted me to do ultra high field as well, and there's many other circumstances in this, but if that would have been permitted, then yes, I would be glad to embrace it. But my life sent me this way for whatever reasons, you know, and so I embraced it and
you were following the truth. What you considered, I mean, your research brought to certain problems, and you saw that problems, and you went really to the ground.
Right.
You know? Yeah.
Right. And I think now people are starting to understand that there is problems with Kirchhoffs Law, even though I published, you know, I use unconventional means, right?
Yeah, so you're taking that video. I found it a really great idea. I mean, because, I mean, it's such a simple experiment. We could do it with a video camera and some simple materials, and it's okay. I mean,
the black bodies can do work, yes.
Yeah.
And I think that, you know, however paths I took, you have to think, you know, if people were in my place, they'd say, okay, well, what paths were really open to him? And I don't blame my peers for this, you know, they don't owe me a path. And then on the other hand, human ideas cannot be suppressed because we have to have an accepted path, right? This would be very terrible for science. So maybe the price I pay is more, you know, opposition, but it's okay. But at least the ideas can come out, and if people are careful, they'll see that my papers are being cited now. It's rare, but sometimes they're cited in good journals by good people, and you know, so people are aware of what I've said, and I also realize that just because a paper is not being cited, it doesn't mean it hasn't been read and considered, and it can take many years before, okay, we're aware of this, but this is just too much dessert for us today. We're going to pass on that, but maybe later on they'll accept it. So put the idea out, and then let people think about it. Don't be in a rush. And you know, they have their careers and their wives and their children, and they have to make this transition to a condensed sun, which really changes all of astronomy. You know, I understand the consequences.
Coming back to that force, that in your character, the strength you had in pursuing your path. I mean, one would ask psychologically, where does it come from? You mentioned your trips as a teenager, but certainly your parents were afraid when you're traveling alone in Canada. So do you see a role of your parents here?
Of course. I mean, my father. I mean, well. My mother, I'll start with my mother, because maybe all good things learn from our mother first. But yeah, my mother was she didn't have a university education, but she always valued, you know, learning and encouraged her students, her children to learn and study, do your homework and try to excel in school. And she also had a great belief in the truth. And following the truth, and you don't tell lies and so on. And
yeah, truth it's an important topic in today's science. I think if you got a good concept of truth in your childhood, that's a good preparation for being a scientist.
But when I was a young man, you know, I didn't really understand this importance. So this is a danger of being intelligent, and I'm not saying that I'm the most intelligent. I think I work hard, I read a lot, but let's say I'm reasonably intelligent, and I think that's a danger of being intelligent, is that when I was young, you know, I learned to discuss any side of any issue, you know. If you pick a side, I'll pick the other side, and it was just an intellectual game to win the argument. But, you know, I did this, I was married when I was 19, and I married a fantastic person, and you know, one time I was discussing with my wife, and she had a certain position, and I had another one, and just intellectually, you know, I was able to formulate an argument which seemed very reasonable, and my wife, you know, she just started crying, and she said, you know, Pierre, I don't believe you really believe that in your heart, and that's where I started this
very smart, you know,
very, very important transformation that took place in me, that you know, if you have intellect, you also have to bring it to fight for the proper things, and not just because you're intellectually capable doesn't mean that every argument you have to sustain because you can do it intellectually. You have to find the truth. So this was a big transformation which I owe to my wife. You know, had I not married her, you know, even though I had the influence of my mother, it was really my wife that shaped me into. We married so young. I say, well, we were almost babies still, and you know, and then she shaped me into understanding how to use your intellect for good. So that's for me, you know. So science is about truth, and even if you destroy yourself because of it, you have to do that sometimes. Like, so putting your head in the magnet, you know, when everybody said, well, this might hurt your brain or whatever, so, you know, so you go ahead and put your head in it because you believe this can help mankind. Or, you know, radiology.
It reminds from the ancient architects, we were supposed to sleep under the bridges,
Yeah, so this reminds me, you know, about radiology, you know, that you know, today, how many people get cardiac catheterization? You know, where they actually put a catheter in the heart. Well, the first experiment, you know, the person who conceived it, he actually put the catheter in his own heart and then took an X-ray, and that's how we know that this happened, that we could do this. So sometimes, you know, you have to, if you believe in something, then there's a price to pay. You know, you can't. You do have to.
You have to
sacrifice.
Put skin in the game. Yeah.
Maybe put skin in the game, but you have to be willing to sacrifice because it's important. And this is, you know, sometimes as a professor or a scientist, we have many forces, right? We have our colleagues that you want them to respect you. You'd like to have a nice retirement party with lots of students and these types of things. But sometimes you'll be deprived of this because you chose a path, and this has consequences. And sometimes when you follow science, well, maybe this will have, you know, you won't have grant money or students or whatever. So, you know, if I write a grant on the sun, I mean, it's unlikely that people at NSF will say, yes, let's fund Pierre to work on his model of the sun. But maybe a few years from now, in the next generation, then people will be funded to work on these ideas. So that's okay, you know. So there's some sacrifices, and you have to be willing to take those, you know.
Okay. So, but who brought you a little bit towards the medical direction in your life? I think it was your father.
Yeah, it was my father, yeah. So my father, I mean, he's an interesting person, and he also taught me something about, you know, I know your father was a grand chess master, and, you know, I when I was young, my father taught me how to play chess when I was 5 years old or so, and we'd play on Sundays, and my dad had very strict rules. If I would win, if I would lose, I would have to wash his feet. And people say, "Oh my gosh, this is terrible today." They say, "Oh my gosh, how can you raise a child this way?" You know. But it made me understand the importance of don't touch pieces. You think about your next move, and you really want to win because there's some consequences and of prudence, of prudence when you're playing chess, right? And
you're working out the consequences in your head before you're acting.
Right.
That's very important
So and I actually enjoyed this time that my father took with me to play chess on those Sundays, and even though he's 89 now and coming to the end of his life, and I still believe he would be at chess. He's just brilliant at it. So I'm not that good of a player, but it was a powerful life lesson as well, you know, that my dad was teaching me prudence and that there's consequences to your actions and so on, you know. And then I also, another person, well, my father, before we leave my father, I mean, you know, I said at a conference before that my dad was unique because he was possibly the first white man in North America to be named an Indian chief. And you know, if you know the history of Native Americans, you would understand why this is so unique that a white man would be given this great honor to become an Indian chief. And my dad, he was we lived in Northern Ontario, and he took care of a reservation there, and he helped lower the infant mortality rate. You know, women who were having babies, my dad would go at night, in the middle of the night in Canada, and go to the reservation and deliver the child. And he single-handedly had lowered the infant mortality rate of these on the reservation. And he loved the Ojibwe, so he learned how to speak Ojibwe. He still speaks Ojibwe today. He's a chief, but he can speak Ojibwe. And of course, the Ojibwe people, they made him a beautiful regalia of a chief, which he still has today. I almost consider it a museum piece. My brother is going to have it someday. And so he has this regalia, but he was also a godfather for many of the children that were baptized there on the reservation. That shows how much they loved him, that they would entrust him to become the godparent of their children as a white man. And he tells a funny story I can relate. He tells a funny story of, well, it's not a funny story, but it's an interesting story of what he did for those people. So there was a man, and I won't use their last name. I know the last name very well because my father became a godfather to their child. But and his wife and the man, he wanted to build his house on top of a hill. The view was perfect. It was on the reservation, and he wanted to build this on top of the hill. But the water was at the bottom of the hill in the lake, and his wife had 12 children, and there was no running water. So he would come down. She would come down every day to get water from the lake and bring it up to the house for cooking for her children and washing them and so on. So that created much work for her. So my father, so in Canada, you know, we have a parliamentary system, and the Prime Minister of Canada was from our district, which was Sault Ste. Marie. So my father knew him. It was Lester B. Pearson. And so he wrote to Mr. Pearson about the dilemma of this woman that she had to carry water up the hill. And within like a week, my dad said, you know, 2 people from Indian Affairs showed up, and they installed a pump for her so that she had water brought up, and she no longer had to do this. So these are the kinds of things where my dad, he showed his love of other humans, other people, and of the Ojibwe nation. So there's something about life, you know, it's not really, when you die, you won't be thinking about what great paper you wrote, but the people you loved and that loved you, and I think that's important.
Yeah. Let's make it's a service to humanity also. Yeah, that's what we should do in the first place. Yeah.
And if I can, I guess there's one other thing. When I was a child, this was the age of Bruce Lee and so on. So every little boy, they wanted to learn martial arts, and I had the privilege of being taught by someone who was he was from Korea, and he was a real 6th degree, recognized 6th degree black belt. And something happened one time, and he loved me as a student, and we had a very small class because he worked full time in the mines, and then on a few times a week he taught us taekwondo. And something happened which I don't need to recall, but at this time I decided to quit. I was going to quit taekwondo. And so I went to his house and I said, I'm quitting. And he said, okay, you can quit, but you'll never be able to start again. So of course, a few months later, you want to start again. And he loved me. I mean, we spent much time together. He was only 28 and I was maybe 14, 15. And when I went back to ask him to start again, he said, no, Pierre, you can't start again.
So that was a very important lesson, not to stop, not to quit in life. And I think you had a couple of important achievements, and your work is well visible at the internet, and your talks and your papers. And I would thank you again very much for providing this really interesting insight in your work. So thanks again.
Okay, well, thank you for the interview.